Hello, my name is Lisa Pepnick, and this is my Physics 2 Lab 5, where we looked at the magnetic braking with Faraday's law. So a quick introduction to the slab. In the slab, I dropped a bar magnet through a conductive tube of aluminum foil, and I observed the effect on the magnet's motion. And then I also modeled this experiment using a Glowscript computational model for it. And then some of the main physics concepts included Faraday's law, magnetic fields or magnetic dipole and induced currents, Ohm's law, Lenz's law, and then updating velocity and position equations in my computational model. And then the main results of this experiment were that the bar magnet was slowed down and fell slower to the ground than it should have due to the force on the bar magnet from the loop that opposed gravity. So I wrote out some of the main equations that were used in this experiment. I don't need to go through each of them separately, but all of these were used in my Glowscript model in order to model the motion of the magnet through the tube. And they include the magnetic force, the change in flux over time, how to calculate EMF and current, and then the force on the loop and the force on the magnet from the loop, which is opposite and equal according to Newton's third law. So these are the results of the physical experiment. The length of my tube was 0.32 meters, and then the inner and outer radius were 0.02 meters and 0.026 meters respectively. And the mass of the magnet was 0.024 kilograms. The magnetic dipole moment we calculated in lab 3, and this was 3.2 Newton meters per Tesla. And the average time taken to fall through the tube was 1.26 seconds as calculated from 5 different trials. And then the time found by my Glowscript model was 1.32 seconds, which is pretty close to what actually happened. So now to go through my Glowscript code, at first I had to update all of the physical constants. And then I calculated the dipole moment of the magnet, just like I did in lab 3. And then on the bottom, I calculated the change in flux over time through each ring due to the falling magnet. So the tube was separated into a bunch of rings that each had a current. And this was using the equation that I mentioned before a couple slides back. So this was just putting this into Glowscript. And then this calculated the typical B field of each ring, and then I added all of them up. And this was also using the same equation that was a couple slides back, where we had the force on the ring and then the force on the magnet was in total the force on the magnet from all the induced rings and the gravitational force. And then on the bottom, we have the updated velocity and position equations in order to model this in Glowscript. So here was the result. We can see the magnetic fields that were produced on the left, the blue and red, and as the magnet fell through the loop, they moved down with it. And then we also have a velocity versus time graph that was produced from our Glowscript model. So interpreting the simulation, here are some of the questions that I answered. It says the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicates current flowing in the opposite direction. Which color corresponds to clockwise current and which counterclockwise, and how can you know? So red is counterclockwise and blue is clockwise because this is the combination that would slow the magnet down. And then what happens to the dynamics of the system when you flip the magnet around? Well, this actually made no difference in the model, and I physically tested this and it had no effect. So then how does my total time and tube of your real world system compared to that of your computational model, and how might the computational model be made more accurate? So the real world time was slightly shorter, it was 1.2 seconds versus what I found in my computational model, which was 1.32 seconds. And the computational system can definitely be made more accurate by dividing the tube into more loops of current or by accounting for the air resistance on the magnet as it falls down. And then lastly, what is the shape of the velocity versus time graph tell you about the forces acting on the bar magnet? Well, if we look back at it, we can see that the velocity was increasing at first, and it slightly decreased, and then it was constant until it started decreasing again. So in that constant time period for about a second, we can see the force on the magnet, the gravity going down, and the force from the loops going up balanced out. And so the net force for just a second was 0, and that's why the velocity was constant. So lastly, some additional questions. What if the resistivity of the conductor was reduced as close as possible to 0? How did the dynamics of the falling magnet change? So the braking force would actually keep increasing on the bar magnet until it would balance the gravitational force, and this would prevent the magnet from falling at all. And then what if holes or slots were cut to the tube? How would this affect the ring currents in your model? So this would actually disrupt the flow of current going through the tube, meaning the braking force would probably be not as strong since less current is able to flow through the tube, and the magnet would fall through faster since there would be less opposition to the force of gravity going down. So this was my Physics 2 Lab 5, and thank you so much for listening.